Hello and welcome to Video Podcast 9.1. In this podcast, we will overview Earth's oceans and ocean salinity. Let's start by considering the four ocean basins, which actually cover 71% of Earth's surface. The first ocean that we'll consider, which is the largest ocean and has the greatest average depth, is the Pacific Ocean. In fact, the Pacific Ocean is so big that all of Earth's land combined can fit within the Pacific Ocean with room to spare. The second of Earth's four main ocean basins that we'll consider is the Atlantic Ocean. The Atlantic Ocean is about half the size of the Pacific Ocean, and it's also not as deep. Another important feature to note about the Atlantic Ocean is that it's a much narrower ocean than the Pacific Ocean, and it's also bounded by nearly parallel continental margins on its sides. The third ocean we'll talk about is the Indian Ocean. The Indian Ocean is slightly smaller than the Atlantic Ocean, and it's predominantly located in the southern hemisphere. If you look at the graph shown on the screen, most of the area of the Indian Ocean occurs below the equator. The last of the four oceans that we'll discuss is the Arctic Ocean. The Arctic Ocean is about 7% the size of the Pacific Ocean, and it's located entirely in the northern hemisphere. There's a couple important things to consider when looking at the images shown on this slide. When we compare the northern hemisphere to the southern hemisphere, notice that the majority of Earth's landmass occurs in the northern hemisphere. In the southern hemisphere, the surface of our planet is predominantly water. When you contrast that with what you see in the northern hemisphere, where almost 40% of the surface is land, it probably makes sense why we call the northern hemisphere the land hemisphere and the southern hemisphere the water hemisphere. I also want to call your attention to this graph shown on the screen. When you look at what's going on between the latitudes of 45 degrees north and 70 degrees north, you'll notice that there's actually more land than water. But now let's shift your attention to what's happening in the southern hemisphere between the latitudes of 40 degrees and 65 degrees. Between these latitudes, there's almost no land at all. That's really important because with no land in this region, there is nothing to interrupt oceanic circulation, and there's really nothing to interrupt atmospheric circulation either. Now let's shift our attention to salinity, which is defined as the total amount of solid material that's dissolved in water. Put simply, salinity is the saltiness of our oceans. We're most familiar with expressing things as percentages, and if you look at the breakdown of the dissolved components in ocean water, you will see those expressed as percentages. However, when we talk about the dissolved substances in seawater, we typically express those in parts per thousand. And to represent parts per thousand, we typically use a percentage sign with an extra O in the denominator, as shown here. What's important to note is that most of the salt in seawater is sodium chloride. We actually learned about sodium chloride when we talked about rocks and minerals. And you may recall that the mineral halite is sodium chloride. However, keep in mind that in seawater, the sodium chloride is dissolved, meaning that we see sodium ions and chloride ions. Now, a question you might be asking is, where does the salt in seawater come from? Well, there's two primary sources. The first of which is the chemical weathering of continental rocks. Specifically, a lot of the dissolved components get carried through rivers and streams and dumped into the oceans. A second source of sea salts is Earth's interior. Through volcanic eruptions and what's known as outgassing, many of the dissolved components in seawater get into the seas through geologic processes. Now let's shift our attention to the processes that affect seawater salinity. When you consider all of the latitudes on planet Earth, you'll notice that the salinity varies from location to location, as does the temperature of the ocean water. Common sense probably tells you that the temperatures for ocean water will be highest near the equator, and that's true. That's because most solar energy is concentrated at or near the equator. But when you look at the blue salinity plot for different latitudes, you might notice that it takes on an M shape, and that's a little bit harder to explain. Before I explain the salinity graph, it's important that I state the oceans are very well mixed. So seawater components are basically constant across the globe. Therefore, the changes in seawater salinity are caused by the changes in water content of the solution. Specifically, we're concerned with the addition of fresh water and the removal of fresh water. And those two processes are what really cause variations in ocean salinity. Let's start by considering the addition of fresh water to the ocean. In places where fresh water is being added to the ocean, there will be a decrease in salinity. As an example, I want you to take a look at where the Mississippi River dumps into the Gulf of Mexico. In this image, you'll notice that most of the Gulf of Mexico is shaded yellow or orange. And yellow and orange correspond to an ocean surface salinity that's somewhere between 36 and 37 parts per thousand. However, take a look at that little band of green that you see extending right there in the middle of the Gulf of Mexico. That green decrease in salinity that you see is caused by the Mississippi River. An even more drastic example of how runoff affects the salinity of the oceans can be seen where the Amazon River dumps into the Atlantic Ocean. That really bright blue trail shown here, that relatively low salinity squiggle, is significantly lower than the salinity surrounding that region. Another important fact is that salinity tends to be highest in regions where there's not much rainfall, but the evaporation rates are fairly high. Take a look at our planet's dry subtropical latitude regions, which occur near 30 degrees north and 30 degrees south. The 30-degree latitudes correspond to high-pressure regions on our planet, and high pressure usually corresponds to sunny, dry conditions. These areas usually receive low amounts of precipitation, but because they receive ample sunshine and warmth, the evaporation rate of water is quite high in these areas. So with a lot of water evaporating off of the surface of the ocean, but not a lot of water falling back into the oceans in the form of precipitation, the salinity of the ocean tends to be quite high in these regions. It shouldn't be surprising that at or near these 30-degree latitudes, most of Earth's deserts reside. Now let's shift our attention to the polar regions. The salinity will vary seasonally near the poles. Specifically, during the winter months in the Arctic, seawater will freeze and form sea ice. Now, when this water freezes and sea ice forms, most of the salt is left behind in the water. Therefore, when the temperatures start to drop and more sea ice starts to form, the salinity of the seawater will increase. However, when the summer months roll around and the temperatures gradually warm, some of the sea ice will melt back into the surrounding ocean water. That melting ice has a diluting effect, and the salinity of the seawater will decrease during the summer months. The final consideration in this video podcast is climate change, ice caps, and acidity. Due to the burning of fossil fuels, we are adding enormous amounts of carbon dioxide to our atmosphere. However, climate change doesn't only affect the atmosphere, it also affects our oceans. In fact, about 33% of human-generated carbon dioxide ends up dissolved in the ocean. As this graph shows, atmospheric carbon dioxide levels have been increasing, and they've been increasing since the Industrial Revolution. But it's also important to note that as carbon dioxide levels in our atmosphere have increased, so too has the amount of carbon dioxide dissolved in our oceans, which is shown by the blue plot on this graph. Now, as dissolved carbon dioxide in the ocean increases, the pH of our ocean decreases. What that means is our oceans are becoming more acidic as more carbon dioxide is dissolved in seawater. Increased amounts of carbon dioxide in the ocean can actually affect many organisms' ability to produce shells and other hard parts, because those organisms rely on the availability of the carbonate ion in order to produce their hard parts. It's also important to note that as our planet warms, the amount of sea ice forming near the poles is dwindling. The median sea ice minimum between 1981 and 2010 is shown by this blue line on this image, and the 2015 sea ice minimum is shown by this red outline. The decreased amount of sea ice near the poles impacts both the salinity of the ocean water in these regions, as well as the global circulation of ocean water. I'll talk more about the circulation of ocean water in a future vodcast, but for now it's important to emphasize that the effects of climate change extend beyond just our atmosphere. Okay, that's the conclusion of this video podcast. In our next video podcast, I'll consider the variations in temperature and density with ocean depth.